Hello, my name is Kip Nieman, and I'm here to present on neural network-based model predictive control of residual stress in powder bed fusion for the 2020 Michigan Space Grant Consortium Fall Conference. This research addresses several limitations in long-term space exploration. These include the limited supplies of metal replacement and repair parts and tools in remote space locations, the expense and fuel cost of transporting heavy cargo shipments into Earth orbit, and the creation of metal parts by other means, such as casting or subtractive manufacturing, which would not be cost efficient and thus would be challenging to implement into space. Additive manufacturing would offer significant benefits for sustained visits in space. This capability would offer the speed and flexibility to produce parts for a wide variety of situations, which would allow for significant improvements in safety in a sense of dealing with short-term emergency needs for unique parts or tools, and sustainability in the long term. In addition, given the ability to transfer smaller overall amounts of raw material instead of copies of a wide variety of completed parts, this will reduce the weight of cargo shipments into Earth's orbit. The specific kind of additive manufacturing considered in this research is known as powder bed fusion, or PBF for short. It is used to produce metal components and is currently used, for example, to create specialty parts in the aerospace and medical industries, among others. It involves a moving laser that melts successive layers in a bed of powder. Between each layer, a new powder layer is swept over and the process is repeated. The resulting residual stress in the part is a primary concern as it leads to warping or cracking, thus requiring heat treatment. This heat treatment requires significant energy and time investments. Any way of reducing or eliminating heat treatment would remove a significant obstacle to performing PBF in space applications, as long baking cycles would be prohibitive due to the significant energy cost. Currently, process parameters such as laser speed and intensity are typically implemented in a trial and error way, which relies heavily on operator experience and involves no feedback during the process. Researchers studied implementing control by monitoring the dimensions and temperature of the melt pool using optical sensors, which only indirectly accounts for residual stress. The hypothesis in this work is that to reduce the residual stress in the final part, PBF can be controlled using advanced control that directly makes predictions of the resulting residual stress. Such a controller requires the ability to predict stress and control the process in a way that constrains it. A form of advanced control is known as model predictive control, or just MPC. MPC is an optimization-based controller that uses a model of the process to determine control actions. For these reasons, in this work, MPC will be explored for use in limiting residual stress. The research challenge in applying this controller is that stress modeling is typically performed via complex and computationally demanding simulations, and that MPC requires real-time prediction of the stress to constrain it. To address this challenge, a reduced-order modeling strategy will be implemented for the residual stress. One reduced-order model is called a neural network, which uses a series of mathematical neurons that can be trained to recognize patterns in data. Given the previously stated considerations, the objectives of this research are as follows. The first step is to create a model of the process of heat transfer and solid mechanics using the ANSYS simulation software. The next step is to use a model reduction method, such as a neural network, to create a computationally efficient model of stress. Thirdly, model predictive control will be implemented into the ANSYS simulation. This controller will predict the residual stress using the reduced order model and use the prediction to constrain the stress in the process. Finally, the residual stress under classical proportional integral derivative, or PID control, and MPC will be compared. The progress so far consists of adapting previous work to create an ANSYS-coupled transient thermal and structural simulation modified with custom ANSYS parametric design language, or APDL code. This code allows for custom functionality. These functionalities include a moving Gaussian heat source that represents heat applied by the laser, the inclusion of nonlinear material properties to represent the powder, liquid, and solid phases, as well as a method of transitioning between the phases depending on the temperature, and a method of storing the positions of the solid elements from the thermal analysis and removing the powder phase when transitioning to the structural analysis. Figure 1 demonstrates the kind of temperature profile that is simulated, and Figure 2 shows the x-direction normal stress from an example of the buildup of the first layer on a base plate. Our next steps to continue with the project are to develop a neural network to represent the process and to implement the controllers into the simulation. Thanks so much for taking the time to listen to my presentation.